So here's a final sample homework problem. You have one of these in WebAssign. And this is page 389, number 33, section 5.2. This illustrates what happens when a function on our interval of interest drops below the x-axis, and what that means for the value of the definite integral. Let me emphasize again, a definite integral from a to b of f of x dx is the limit of a sum. We can interpret that in terms of areas. So it's the value's a number, specific number. An indefinite integral is just a function. It's the most general antiderivative. And in a future lesson, we'll see the connection between these two. These two mean very different things. But obviously, since we're using similar notation, they've got to have some connection. Okay. Evaluate each of the four definite integrals below by interpreting them in terms of areas. So I've got the definite integral from 0 to 2 of f of x. 0 to 2. So the function from 0 to 2 is totally, notice, above the x-axis. So the definite integral from 0 to 2 is just the area, this area, because the function is above the x-axis. So is this a shape that we can find the area of? Well, isn't it a rectangle? See the rectangle? Plus the triangle on top of that. So what's the area of the rectangle? Well, the base is 2, the height's 1. That would just be 2. Right? 2 squares here. What's the area of the triangle? That's 1/2 base times height. So the base is 2. The height is 2. 1/2 of 2 times 2 is just 2. And notice this bigger rectangle up here is 4, and I've got half of that. So the area of this triangle is just 2 also. So the definite integral from 0 to 2 of f of x dx is just 4 square units. That's this shaded area. Okay, how about from 0 to 5, the definite integral of f of x from 0 to 5? Well, couldn't I make use of my previous problem? I could say that's the definite integral from 0 to 2 plus the definite integral from 2 to 5. This is actually a theorem in your book. In section 5.2. In fact, it's theorem 5 on page 387. Page 387, theorem 5, talks about how you can divide this interval 0 to 5, maybe from 0 to 2 and 2 to 5, etc. That's just common sense, isn't it? But that's a formal theorem in your book, page 387. Okay, we already know the value of this first definite integral from 0 to 2 was 4. Now let's figure out the value from 2 to 5. Well, from 2 to 5 is just, notice from 2 to 5, the function is still above the x-axis. So the value of the definite integral is just the area between the graph and the x-axis. And from 2 to 5, I could divide the region into what? This rectangle. And then this triangle. Well, the area of my rectangle, the base is 1. From 2 to 3 is 1. The height is 3. From 0 to 3, that's 3. So the area of this checked rectangle here in the middle is base times height. 1 times 3 is 3. Now, what's the area? So this area is 3. Now, what's the area of this triangle? Area of a triangle is 1/2 base times height. The base is 2. The height's 3. 1/2 times 2 is 1. 1 times 3 is 3. So my answer to the B part, the definite integral from 0 to 5 f of x dx is 4 plus 3 plus 3, which is 10 square units. 10 square units is the area of this entire shaded region on top. Okay, how about C, the definite integral from 5 to 7? Now notice from 5 to 7, the function drops below the x-axis. Okay, so, and in fact, the function is entirely below the x-axis. So the value of the definite integral is just going to be the negative of this area. Remember, area is always positive. But since my function drops totally below the x-axis on that interval, the value is the negative of the area of that triangle. The area of that triangle is, the base is 2. Area of a triangle is 1/2 base times height. The base is 2. In other words, from 5 to 7 is 2. And the height is from 0 to -3. That's 3. The height of that triangle is 3. So the definite integral from 5 to 7 of this function is just -1/2 times 2 times 3, which is -3. That says that there are 3 units of area below the x-axis from 5 to 7. Now, how about the definite integral from 0 to 9? Okay, now notice from 0 to 9, in other words, from here to here, from 0 to 9, the function sometimes is above the x-axis, then sometimes it's below the x-axis. So the definite integral from 0 to 9 of the function is going to be the total area above the x-axis minus the total area below, the net area, in other words. Well, the total area above the x-axis, we found out from part B, was 10. That's the total area above the x-axis from 0 to 9. That was the area from 0 to 5. That was 10. But from 5 to 9, the region is below the x-axis, so I have to subtract that area. So I subtract 3 to get from 5 to 7. And I've got to figure out how much more I subtract to get from 7 to 9. So from 7 to 9, all right, from 7 to 9, I can divide that piece into what? Into a triangle and a square, right? Got a triangle and I've got a square. What's the area of that square? One dimension is 2, the other dimension is 2. 2 times 2 is 4. The area of this square is 4 square units. Remember, area is always positive. But this region lies below the x-axis, so its contribution to the definite integral is negative. I've got to subtract away 4. Because the square of area 4 lies below the x-axis. How about this triangle? What's its area? 1/2 base times height. Well, the base is 2. The height is 1. 1/2, 2 times 1 is just 1. So I subtract away 1 because the area of this triangle right here, the area of that triangle is 1. So my total value of the definite integral from 0 to 9 is 7 minus 4, which is 3, minus 1 is 2. What does that mean? Look back now at this entire graph. Everything's shaded now. There's 2 more square units of area above the x-axis than below the x-axis. That's the net area. My graph's not perfect. It might look like maybe the answer should be -1 or something from my graph. But I think you'll find it believable that there's 2 more square units of area above the x-axis than below.